that's one way of helping to kind of piece together what the antiderivative is going to be. What you should have gotten here, and I'll kind of talk through my thought process of getting an antiderivative of this so you can kind of see how the thought process works. To the negative second, so add 1 to the exponent. That had to be an x to the negative first. Let's see, which would create a negative 1 hopping out in front, which is exactly what happened, so we're good. The 3x to the negative fourth, so that means an x to the negative third had to be there, which would cause a negative 3 to hop out in front, which is what's there, so we're good. We should start with a positive 1, and then the negative 3 multiplied will create the negative 3. And then antiderivative of 12x, that's got to be 12. Or antiderivative of 12 has got to be 12x. Plus c. So let's rewrite that here. Put our negative exponents back down on the bottom. 1 over x plus 1 over x cubed plus 12x plus c. And now we're going to use our initial condition, which is that y equals 3 when x equals 1. And we're going to use that to solve for c and figure out what c is. So y is 3. We put 3 in for y. And we're going to put 1 in for x. This is 1 plus 1 plus 12 is 14. So that means c has to be negative 11. So our final answer is going to be that same function, but now instead of the plus c, we know what c is. Instead of plus c, c is negative 11, so we're going to write minus 11. There's our final answer. Questions on that? All right, let's do a couple more. A couple of you had trouble picking out what these antiderivatives were. So now we'll see what it comes out to be. One over 1 plus t squared. That is the derivative of inverse tangent. And we're using t as our variable instead of x, so inverse tangent of t. Plus, this is our derivative rule of two to the t. Because the derivative of 2 to the t is 2 to the t times natural log of the base. And that's what's going on there. We have a 2 to the t times natural log of the base. So we had to start with 2 to the t. Plus c. And now we're going to be using our initial condition. When t is 0, y is 3. So we're going to put 3 in for y. and then we're going to put 0 in for t. And we got to make sure that we are careful and know what each one of these are. Inverse tangent of 0. Well, what angle is going to have a tangent of 0? Oh, it's 0. 2 to the 0, it's 1. So this is 1 plus c equals 3, so that means c equals 2. So our final answer here, we're going to write our function, except instead of plus c, we know what c is now. It's 2. Hopefully we can make out where our t's are and where our pluses are. Questions on that one? We're doing one more. Once again, I'll give you about 2 minutes to try this one. We're using V. Just to mess with you, we're not using X and Y anymore. But the process is still going to be the same. Antiderivative of secant tangent. Well, secant tangent is the derivative of secant. Antiderivative of e to the t, well, that's easy. That's e to the t. Antiderivative of 6t is going to be 3t squared plus c. And so let's plug in. V is 5 when t is 0. And so let's do some evaluations here. Oh, hey, that's what's going to happen. Secant of 0 is cosine of 0 flipped. That's the way I think about secant of 0. So take cosine of 0 and flip it. And so cosine of 0 is 1. Flip it, still 1. E to the 0, 1. This is 0. And so that's going to create C being 0. So that means no constant. Final answer, V equals 4 secant of t plus e to the t plus 3t squared, no plus c. All right, questions on any of that? So when we start looking at kind of larger free response problems, especially on functions where they give you on kind of more word problem type things, where they give you the derivative function or a rate function, and they want you to work backwards to get to the integral. Part of what they're going to do a lot of the time is they're going to give you an initial condition like this. They'll say at time t equals 0, maybe they'll give you like the rate that a water tank is filling up. And they'll say at time t equals 0, there were, I don't know, 5 gallons of water in the tank. And so that's your initial condition that you want to factor into the rest of the problem. So that's one of the ways that a lot of these type of problems are going to come up. So let's make sure that we've got how to write that as an integral. So we are not doing antiderivatives this time. So this will actually be easier. In fact, we don't know how to do these antiderivatives, so don't even worry about them. What we're going to do, I'm going to show you how to do part A, and then you're going to do part B. I'll just tell you what the answer is, and then I'll talk about why that's the answer. I want to make sure you understand why that's the answer, and then it's going to be really easy to do any of the other problems we run into. The answer to this problem is that. Okay, let me break this down a little bit. First off, since I'm putting x in the upper bounds of the integral, I want to put a different variable inside the integral, so that's why I switched it to t and dt. Okay. Now the key part of this is going to be the fact, the reason that I put 1 as my lower bound is so that I can make sure, no matter what the integral and the antiderivative and all that mess that I would have to figure out in the calculator turns out to be, I can control at least one point. I can control what happens when x is 1. Why do I know for sure what happens when x is 1? When x is 1, what happens here? 0. Of who cares? This is 0. So that's why I chose my lower bound as 1, so that when I plugged in 1 for x, I was getting an integral from 1 to 1. And then I could just say this part will be 0, so let me put a plus 5 here, and ta-da, y is 5. Like magic. So see if you can figure out what the next one is. Fill in the spots there. First off, the upper bound we want to be x. And we want to control what happens when x is 2. And so we're going to put a 2 down here so that this will all be 0 when x is 2. And then to make f of x equal 9, well, we just controlled that this was 0 plus 9. And there's our answer. Right? Questions on that? All right. Let's review a slope field real quick. Let's do part B. We'll talk through part B. At least a couple of them. Just so that we remember how slope fields work here from a whole week ago when we did them. dy dx equals 2x plus y. So let's see. We'll start at 0, 0. When we're at 0, 0, slope is 0. Anywhere that's undefined? No, not this time. And we can start going down the line. How about when x is 1 and y is 1? Our slope is 3. So we're going to draw a slope of 3. How about when x is, how about at negative 1, negative 1? It's going to be negative 1. Or no, it's going to be negative 3. Sorry, negative 3. I can't add today. How about when x is negative 1 and y is 1? When x is negative 1 and y is 1, that's going to be negative 2 plus 1 is going to be a negative 1. When x is negative 1 and y is 0, that's going to be a negative 2. When x is negative 1 and y is 2, what will dy dx be? So right here. It's going to be 0. So that's going to be a negative 2 plus 2 is 0. And then we keep working on down the line. When x is 0, then we only need to worry about y. So we just take the y coordinate. So 2, 1, 0, negative 1. When x is 1, well then we're going to take 2 and then add the y coordinate. Because that will result in 2x being 2 when x is 1. So we're going to take 2 and then add the y coordinate. 2 plus 2 is 4. 2 plus 0 is going to be 2. 2 plus negative 1 is going to be... There's a lot of different ways to organize which way you draw it. Keep x constant and then see what happens when y changes, or keep y constant, what happens when x changes. Sometimes there are patterns like going diagonally. And so maybe you notice one of those diagonal patterns and that helps you with it. Right? There's a couple different ways. Whatever helps you. If you just need to make a big table, then you need to make a big table.